Okay. Okay. Okay, we start present. Okay, so chapter 6, first law of thermodynamics. So, okay, I think I have mentioned about this kind of briefly about this law before in the beginning, I think, because in this aerothermodynamic course, we will learn I will introduce to you two laws of thermodynamics. Means the main principle law in thermodynamics. So the first one is today. It's going to be today, and the next one, second law, is in the second half of the semester. Okay, inshallah. Okay, so the first one, first law of thermodynamics, basically in general, what this first law of thermodynamics said is that the energy cannot be created nor destroyed. Okay, energy cannot be created nor destroyed. Okay, but energy can be transferred from one form to another form. Okay, means you can change the form of the energy from thermal energy to mechanical energy, from kinetic energy to potential energy, right? From what kinetic energy to elasticity. Elasticity is potential energy. You have seen last week the work, for example, the work that we put in spring, kan, spring or getah, rubber. Okay, so that is elasticity potential energy work, okay, that we give to the spring or to the system, and then the material or the spring will move. Okay, so that is from potential elasticity potential energy to kinetic energy, and there's a lot more. Okay, etc. Like solar energy, we have solar, sun. Sun is the main source for heat. Okay, from heat, thermal, so it will be changed to we can transfer the heat from the sun to electricity by using solar photovoltaic PV. Okay, so first law of thermodynamics, that is in general what the what does this first law mention. Okay, so basically from the definition, okay, definition that the energy cannot be created nor destroyed. From that, we can derive the energy balance equation. Energy balance lah. So usually we want to when we want to evaluate the performance of a system or of a process, we need this energy balance equation or expression. Okay, so this energy balance is derived from this law. When I said the energy can only be transformed from one part to one part, so from there we derive the energy balance equation for a system. Okay, start. Okay, that is my introduction, mukadimah. Okay, sepatutlah silap slide. Okay. So this is the learning outcomes or the objective of this chapter today. Actually, I don't have too much slides. This chapter only I have around 15 je. And then 2-3 slides, 15 or 16, something like that. And then 2-3 slides tutorial exercise. So we will do. We try to do more exercise today, tutorial today, because I think this chapter needs more exercise, more example, more practical. I mean practical in terms of exercise, not lab, but practical tutorial, something like that. Okay, because actually the principle or the equation, the theory is just short and simple, and from the theory how you're going to apply it in the process, in the system, that is what we are going to do, inshallah, today. Okay, so these are the point or the things that we are going to see today. Conservation of mass. Actually, this one also I have mentioned conservation of mass, because from this conservation of mass that we derive also the conservation of energy, which is the first law. Okay, so conservation of mass principle, steady and steady flow volume, conservation of energy. Okay, so conservation of energy, the statement of the conservation of energy is the same as the first law. When we say first law is that energy cannot be destroyed and created. Okay, so that means that the energy is conserved. Okay, it cannot be destroyed, so it is conserved. So the same definition is derived from the first law. And then identify the energy carried by a fluid stream crossing a control surface, potential energy, etc. To relate the combination of the energy and the flow to the property enthalpy. So from this, the definition of conservation of energy, okay, so we can develop, like I mentioned just now, the energy balance of the system. Okay, the fluid, the air, the fluid, the water that goes through a system, right? We can apply this energy balance to the system. Okay, so energy balance include kinetic energy, potential energy, flow work, etc. Okay, we see that. And then solve an energy balance problem for common. Okay, this is the application that is important, especially for you, for whether you are going to work in the mechanical or aerospace background, aerospace career in the future. Okay, so these are the important application. So it means the why, the why, the reason why we learn this thermodynamics, this aerothermodynamics, that because you are going to apply this energy balance problems to evaluate this device. These are the example: nozzle, compressor, turbines. Those are the device within aircraft engine. Okay. And mixers, heaters, heat exchanger also, it can be in the aircraft engine, but heaters, mixers are more application in the power plant. If you, maybe some of you are not going to work in the aerospace area, maybe you are going to work more on the mechanical engineering area, so you can apply all this energy balance in the mixers, valves, etc. Okay, heaters. Okay, so this is the most important part, the application. And then apply the energy balance to general unsteady flow process with particular emphasis on the uniform flow process at the moment. Okay. Okay, so actually the process, the flow can be steady and unsteady. Okay, we will see that. Okay. Okay, so first one, energy analysis of steady flow system. Okay, I repeat, what is a steady flow? Steady. Okay, the definition: a process during which a fluid flow through a control volume steadily. Okay, if you don't understand that, it means that, okay, one definition is that the change in mass and other parameters, mass, volume, like this one, and H is the enthalpy. Okay, I repeat again, H is the enthalpy. Enthalpy it is a parameter to characterize energy. It is the same as the work, heat transfer. Okay, those enthalpy, work, heat transfer, there are in joule or kilojoule unit. Means joule means energy. Joule is the unit for energy. Power, the unit for power is watt. Okay, now you can understand that. Okay, so H is enthalpy, the one of the important parameter to calculate energy of a system. So when we say steady flow process, normally means that that the mass, for example, the mass are independent of the period of the time. Okay, so if you have in the energy balance, the mass, pressure, temperature, those parameters, if in your energy balance equation you have those parameters, the differential of those parameters will be zero, because there is no the parameter pressure, temperature, all of them do not depend on time, on the period of time of the process. Okay. So under steady flow conditions, the fluid properties at an inlet or exit remain constant, do not change with time. Okay, so you do not when they do not change with time. So the normally in the mathematical equation, okay, the differential form of these properties, pressure, temperature, mass, etc., the differential form within time uh, negligible or zero. Okay, so it doesn't depends on time. Okay, under steady flow conditions, the mass energy content of control volume remain constant. Okay. So many engineering systems such as power plants operate under steady condition. So we can actually make assumption, hypothesis that the system or the control volume that we are going to evaluate is in a steady flow. Okay, normally before you okay, one day, okay, in 2 years, you will have to do your final year project. For example, if your final year project concern on this thermodynamic or propulsion area, okay, so normally your study, your the component, the device, or the machine that you're going to study, okay, you have to define first assumption. You have to make few assumption. Okay, hypothesis lah. Biasa kan, you normally in your, even in your at secondary school, you have learned science, you have to make hypothesis. So one of the most important assumption or hypothesis that we have to assume for in this thermodynamic or propulsion system is that we will assume first that the flow, because thermodynamics of fluid mechanics, we have flow of the air or water. The fluid flow is in steady flow process. Normally we assume this, because once we assume this, it will simplify a lot our prediction of performance. We want to predict the performance of the system, right? Okay. Okay, next. So what happened to the mass and energy balance for a steady flow process? So we have this. Okay. Okay. Jap. Okay. Sorry, my mouse is a bit sensitive, so it keep changing slides. Okay. Mass and energy balance for a steady flow process. I think I'm on the correct page. Okay. Okay, so from the definition of conservation of mass and conservation of energy just now, so we have this mass balance and energy balance. Okay, first one is mass balance first. So mass balance is from the conservation of energy, conservation of mass. Sorry, conservation of mass means that the mass is conserved throughout the process. Okay, so when we say that the mass is conserved throughout the process, means that the sum of the mass at the inlet is equal to the sum of the mass at the outlet. Okay, whatever you give at the inlet, because why we need to write the notation sum instead of only m in m1 equals to m2, because sometimes we have several inlet and several outlet. So that's why it is written here, the sum of those mass inlet equals to the sum of the mass outlet. If you have only one inlet and one outlet, then it is easier. Okay, just M1 equals to M2. But if you have several inlet and several piping outlet, so from this from this mass balance, conservation of mass, we consider that the sum of those whole inlet is equals to the sum of the mass flow rate at the outlet. Okay, so from here, we can write this mass balance equation. Okay, rho V1A. Okay, so normally we change the mass flow rate, the definition of mass flow rate to this term: rho density, V velocity, and A is the area. Okay, the area of the fluid flow. Okay, so because it's easier for us to calculate the mass flow rate, because we can search for its density, velocity, the speed of the fluid flow, and the area concerning the fluid flow. Okay, so that is the mass balance. Okay, and then energy balance. So this energy balance is derived from the first law of thermodynamics that's mentioned, that said that energy is conserved. Energy cannot be destroyed, cannot be created. Okay, so energy balance. So we have this energy balance definition. This is very important definition that you have to remember. Okay, so what does energy balance mention? That the rate of net energy transfer by heat, work, and mass. So there are like previous chapter. Okay, there are several method for energy transfer. Okay, energy transfer by heat transfer, energy transfer by work, like potential energy just now, and energy transfer by mass. Okay, mass also can transfer, means that the mass flow rate multiply with the enthalpy mH. So that is energy, still energy. Okay. So the rate of net energy transfer by heat and work and mass equals to the rate of change. Okay, that the first line is the definition. The rate of energy transfer equals to the rate of change of the energy in the whole system. But since we consider that the process can be considered as steady flow, thus this rate of change I mentioned just now doesn't depend on time. Okay, so this rate of change is zero in this steady flow assumption. Okay, so this rate of change is zero. So E in is equal to E out, like the mass balance just now. So the rate of net energy transfer inlet is equal to the rate of net energy transfer outlet. Okay, so this energy balance can be in kilowatt, or it is also can be in joule. Okay, joule per kilogram. Okay, if you don't have the rate of time. Okay, if you can develop this energy. So what energy contained in the process? Normally, Q in is the heat transfer inlet. So energy transfer by heat. Okay, heat inlet. W in is the heat energy transfer by work. Okay, so work input. Normally compressor, we have work input, the electricity that we need to give to the compressor for the compressor to run. Okay, and then energy transfer by mass. Okay, energy transfer by mass is m dot, the sum because of if we have several inlet outlet. Okay, so the sum of mass flow rate times with the theta. So next line, we define the theta. And then equals to Q out, W out, the same thing. Q out, heat rejected, heat transmit. Okay, heat rejected. W out, work output, work produced normally in a turbine. Turbine will produce work. So from this work that we generate electricity, mechanical work. Okay, and then energy transfer by mass. Okay, at the end. So what does this theta includes? Okay, so theta is enthalpy H. Okay, H enthalpy, and V square over 2, that is the kinetic energy. Okay, and Gz is the potential energy due to the acceleration, gravitational acceleration, and the altitude. Okay, once we have the change in altitude, okay, then there is potential, some sort of potential energy, Gz. Okay, so that is the energy balance of a system, general equation. And then uh, this energy balance will be applied to each of the device or system they are going to study. For example, compressor. Okay, so compressor, what is the energy balance for compressor? So you have to look at, does compressor transfer heat or absorb heat? Does compressor needs power, or it produce power? Okay, So we have to, when we apply this energy balance, we have to define all this in each of the device component. Okay, so remember this energy balance, very important. Okay, next, and again, okay, energy balance relation with a sign convention. Okay, okay, so this one, it's so the energy balance, especially heat and work, uh, it has a sign, with positive or negative. Okay, so if the heat input is positive, that means the heat is being absorbed by the system. Normally at the for example, evaporation process evaporates. Okay, so the water or the steam needs receive energy, receive the heat. Okay, heat transfer by energy transfer by heat. Okay, receive the heat in order to evaporates, to boil the water or evaporates the vapor. Okay, so it has to receive some sort of energy, heat transfer. Okay, from the ambient or from the heat source. Okay, so there is a heat positive, with positive sign. If the heat is being rejected, okay, by the system, then the amount, okay, will be the sign of the heat will be in a negative form. Okay, so the same thing as W, work also can be, has signs, negative or positive. Okay, work positive, okay, is the work produced by the system, and work negative is the work input into the system. Okay, so understeady operation, shaft work and electrical work are the only forms of work a simple compressible system may involve. Okay, so this is just an example. We have a shaft work. We can have also electrical from the resistance, electrical resistance work. Okay, those are example of work, a device that can create work and power, of course, work power. Okay, next is the okay. Uh, More okay, one of the application of this steady flow device. Okay, so many engineering device operate essentially under the same condition for long periods of time. Okay, the components of a steam power plant. Okay, the main basic component of steam power plant, we have turbines, compressor, heat exchanger, pumps. Okay, for example, operate non-stop for months before the system is shut down for maintenance. Therefore, this device can be conveniently analyzed as steady flow device. Okay, so therefore, this device, these components, turbine, compressor, heat exchanger, etc., we can assume it as a steady flow. The flow flowing in the device, normally air or water, steam, is in steady flow process. Okay, so we can use the steady flow energy balance just now. Okay, so this is an example of a turbofan, or gas turbine. Okay, so a modern land-based gas turbine used for electric power production. Okay, so this is in power plant, but it's more or less the same as in your aircraft engine, aircraft engine fan, turbofan normally, turbofan engine. Sama je dia punya, lebih kurang sistem dia macam ni. Okay, so a modern land-based gas turbine used for electric power production. This is General Electric LM5000 turbine. Okay, so we have, so I think by now you're already in second year aerospace, so you know the what the figure, okay, of a F1 engine, okay, of or turbofan engine or gas turbine engine. Okay, jangan dah tahun ketiga keempat pun tak tahu lagi gas turbine ataupun engine aircraft tu macam mana, kan. So this is the engine aircraft. So I think second year you must already know the the figure of the engine aircraft. Okay, or gas turbine. Sorry, this one is gas turbine power plant, but it's the same as more or less the same as a turbofan engine. Okay, so you have LPC. LPC is the low pressure compressor. Okay, so you have low pressure compressor here. Okay, so this is compressor. Yang tak tahu, this is compressor. So if you don't know what compressor look like, it looks like this. Okay, so it has blade. Okay, low pressure compressor. Okay, and then the bleed air collector. So I'm not going to explain this right now. What is air bleed? But you will learn this in propulsion. So that's why after we learn thermodynamics next semester, after you pass this thermodynamic course, you can proceed and continue with propulsion. Okay, so this one about this bleed air collector, we can learn in propulsion. And so basically, actually, the air is bleed from the turbine and being used in the compressor part. Macam tu lah lebih kurang. Okay, so and then high pressure compressor. Okay, so we start with low pressure and then high pressure compressor. So we have multi-stage compressor. And then combustion chamber. Okay, and then high pressure turbine, low pressure turbine. Okay, look at here. We start first with low pressure compressor and then high pressure compressor, HPC. And then for turbine, we start with high pressure first. Okay, because the fluid, the air, is in the state of a high pressure and high temperature. Okay, after exiting the compressor and of course after exiting the combustion chamber, the fluid is in very high temperature and pressure. So that's why we start with high pressure turbine first and then low pressure turbine. Okay. So these are the important components in aircraft engine, but you will learn more in propulsion and of course other course. Okay. Next, okay, so we go one by one. The energy balance of each of the device. Okay, whether it is a device that can be used in aircraft engine or device that can be used in any mechanical device, pump, etc. Okay. So the first one, nozzle and diffuser. Okay, normally we will sketch the diagram or the figures of nozzle like this. Okay, so this is this, we call this as schematic diagram shape of a nozzle and diffuser. Okay, it is not the main figure. Okay, the main the main photo of the nozzle like this. Okay, just simplification. Okay, for schematic figure of a nozzle diffuser. So in future, especially in your FYP, if you were asked to draw, or even in this course, a test or final exam, I might ask you to sketch a schematic diagram of a cycle. Okay, so it doesn't mean that you have to sketch very clearly all the component like this one. Okay, the stage, no. Okay, we sketch the diagram means that we use the diagram. Okay, the schematic diagram for each of the device. Okay, as a like a simplification presentation of this component. Okay, so nozzle we draw normally like this and diffuser we draw like this. Okay, so nozzle and diffuser are commonly utilized in jet engine, rocket, spacecraft, and even garden hose. pipe kan, hose to apa tu, that we have in at our house or at the garden. This also apply this nozzle concept. Okay, so but most of for us more important is that we will have to apply this in jet engine, rocket, spacecraft. Okay, why? Because the function of the nozzle is the main function of the nozzle is to increase the velocity. So that's what we want in aircraft or jet engine, rocket. We want the fluid to be in high speed flow. So that's why we need nozzle normally at the end after the turbine. Okay, after the turbine we have this nozzle, another device nozzle, okay, to increase the velocity of the fluid, the velocity of the air, the mixed air inside the engine, okay, to increase the velocity at the expense of pressure. Okay, and pressure will be expanded, decrease. Okay, and then a diffuser is a device that increases the pressure of a fluid by slowing it down. Okay, so diffuser is opposite of the nozzle. Okay, we increase the pressure but we slow down, decrease the velocity. Normally, diffuser in an aircraft engine, it is located at the air intake, means before the fan or compressor. Okay, before air intake, air inlet of the aircraft engine. So first we have normally this diffuser, and then we compress the fluid, the air. Okay, we have to have this diffuser first, okay, to slow down the air inlet, air intake, and at the same time to increase the pressure. So velocity and pressure is in proportional opposite of each other. Okay, this is also from Bernoulli concept, I think. If you increase velocity, then you decrease pressure. You increase pressure, you decrease velocity. Okay. So the cross-sectional area of a nozzle decrease in the flow direction for subsonic flow and increase for supersonic flow. Okay, this one, this part, we will learn in detail in the last chapter. So means week 13 or week 14, towards the end of the semester, we have a chapter concerning the high speed gas flow. So we will use this nozzle diffuser device application. Okay, and we will look more in detail on the flow process in the subsonic and supersonic flow. At least you understand first, subsonic is less speed. So the Mach number is less than 1. I think you know about Mach number in aerodynamics. I think you have learned that. And supersonic is Mach number higher than 1. More higher than 1. Okay. So we use this nozzle to decrease in the flow direction for subsonic flow, increase for supersonic flow. Okay, but the detail we learn at the end of the semester, the last chapter. Okay, the reverse is true for diffuser. So the same thing for diffuser. So just that the diffuser, the function is opposite of the nozzle. So back to our energy balance. Main topic in this thermodynamics, energy balance. So how are we going to apply this energy balance for nozzle or diffuser? Okay, so the definition energy balance in energy, the rate of energy at the inlet is equal to the rate of energy at the outlet. Okay, so what do we have from the apa tadi? This one. Oh, this one. Okay. This is the general energy balance, the general full energy balance. Okay. So this full energy balance. So from this full general balance, so we see whether nozzle and diffuser contains heat. If does it produce work? Do we have potential energy, etc., etc. If you don't have it, then we consider it as negligible or zero. Okay. So back to this. So energy balance for nozzle diffuser. Do we have heat transfer along the nozzle diffuser? No. The heat transfer is very very small compared to the other energy, enthalpy and kinetic here. Uh, whether the heat transfer in or out is very small or zero, so we can neglect that. And then there is no power output or power input given to the nozzle and diffuser. It doesn't produce work like turbine, even though it can decrease the pressure, but it doesn't produce work. Okay, and potential energy, PE is potential energy, is nearly zero. So we can neglect. Potential energy here means that the altitude, okay, the level of the inlet of the nozzle and the level altitude, the height of the outlet of the nozzle. Maybe there is a slight different, but the difference is too small compared to other term of energy, kinetic, etc. So that's why the potential energy can be negliged. Okay, nearly zero. Okay, so what do we have left? We only have left with the energy transfer by mass, which is enthalpy. Enthalpy is the Enthalpy actually is U plus PV. U is the internal energy, means the change of energy due to the temperature and pressure. So there should be enthalpy. And then V square over 2 is the kinetic energy. Of course, since the function of the nozzle is to increase the velocity to a high speed flow, so the kinetic energy must not be negliged. So we have to include this kinetic energy because that is the most important part, the function of the nozzle. You want to increase velocity, so kinetic energy tak boleh lah abaikan. Okay. Usually this kinetic energy is big compared to others, potential and heat transfer. So that's why we neglect the potential and heat transfer. Okay, so this is energy balance for nozzle and diffuser. Please remember, so enthalpy plus kinetic energy. Okay, but if you do one day, if you do experiment or you do like your FYP project, okay, you do case study, maybe you find some sort of energy or heat transfer or potential energy within the nozzle and diffuser. Maybe you find some sort of this energy, but this energy should be very very small, not important, not significant compared to the kinetic energy. It's not that there is no totally null, okay, but it is negligible. They are negligible. Okay, especially if you want to simplify our calculation, our assumption. Okay, so we can assume like that. It is acceptable. Okay, but if you want to precise, detail your calculation, your prediction of performance, then you have to include those energy, potential, etc. Right? Okay, especially if you're doing your thesis, PhD, postgraduate, that one maybe you cannot just neglect, or if you neglect, then you have to reason out. Okay, argue your assumption. Okay, next one. Next one is turbine and compressor. Okay. Just now nozzle diffuser, now turbine compressor. So this device, they opposite of each other actually. Okay, so this is the compressor, the figure here, the schematic diagram for compressor. So it is like nozzle. Okay, because due to the, if you see here, why we draw it like this instead of the other way around. Okay, because if you see just now our gas turbine, okay, so actually, okay, the compressor, look at the compressor here, the low pressure compressor, the radius of the blade and the compressor is bigger at the first part, LPC, and for high pressure compressor is smaller. Okay, so that's why we imagine the compressor from high area, the frontal area tu lebih besar, high pressure compressor, area dia lebih kecil. Okay, so that's why the schematic diagram we draw it like this. So if you have low pressure compressor here, high pressure compressor here. So turbine drives the electric generator. So what is the function of turbine? So turbine very important. Turbine drives the electric generator in steam, gas or hydroelectric power plant. So as the feed pass through the turbine, work is done against the blade which are attached to the shaft. Okay, so turbine very important. So in this turbine that we produce power, we produce electricity. Okay, produce power, electricity, the shaft rotate, mechanical power, etc. Okay, so that's why the name, okay, why we call the whole of the engine as gas turbine instead of compressor or heat exchanger, etc. We call it gas turbine because the main output from this device, from this power plant, is the turbine that produce work that we want, electricity, mechanical, etc. Okay, and or for aircraft engine, is the thrust power. But for aircraft engine, turbine has to work with nozzle, okay, to create the thrust power. But for power plant, any power plant to produce electricity, mechanical power, etc., a turbine can produce power work. Okay, so turbine is the one who is going to produce power work, and compressor is the one that is going to use some of this power produced by the turbine to run the compressor again. Okay, because the compressor that is the device that need to work. Okay, so compressor as well as pumps and fans. So pump and fan also consider as part of compressor because the function is the same, just that the objective may be different. Okay, but the function to increase the pressure, to increase the temperature are the same. Okay, compressor, pump, fan. Normally, compressor is used for steam or air, gas. Okay, vapor, air, steam, gas, sama. Okay, pump usually is used for liquid, water. Okay, and those are the liquid. Okay, so that is some of the difference perbezaan lah. Okay, so this device used to increase the pressure of a fluid. Okay, work is supplied to this device. So in order to increase the pressure, compressor needs energy, need some sort of work source, work input to rotate the shaft. Okay, so that's why the work produced by the turbine is being used in the compressor. Okay, a fan increase the pressure of a gas slightly and is mainly used to mobilize a gas. Okay, normally in aircraft engine we have a fan first before compressor, or the fan is the same part, the same at the same position as compressor. So that's why it is called turbofan engine. Okay, this one you will see in propulsion. Turbofan engine, one of the main engine used in for aircraft, for civil aircraft. Okay, so we have a fan. We still have compressor, but at the same time we have fan. Okay, and then compressor to compress gas. Okay, pumps work very much like compressor, except that they handle liquids instead of gas. So pumps is more used for liquid. Okay, to compress the liquid, to increase the pressure of a liquid in power plant especially. So what the energy balance of this compressor and turbine is going to be? Okay, so again the general energy balance, and then we look in the process, we look into the process. So this turbine, okay, actually W out, not the Q out. It's the okay. W in MH1 equals to W out plus MH2. 14 nanti W out. Okay, there is of course some sort of heat transfer, but it is can be it is negligible. So for compressor and turbine, the energy balance, work input usually in the compressor. Okay, so compressor need power to pump the fluid. Okay, and then the enthalpy usually always there. Okay, so and then there is no kinetic energy because there is not much change in change in velocity. Okay, there are no much change in velocity of the air, of the fluid inside the compressor. Okay, so there is no kinetic energy. Okay, and there is no also potential energy, no change, significant change in altitude, gravitational force. So there's no potential energy as well. And Q out plus MH to W out. Okay, work output plus internal enthalpy. Okay, so kinetic energy and potential energy can be negligible. Okay, so this means that for turbine we work output produce work, for compressor work input. Okay, and no change in Q out, or very very small Q out or Q in compared to work done or work produced, work input or work produced. Okay, next component. Okay, 955. Okay, semua datang. Okay, semua ada. All of you are here. Okay, next component is throttling valves or pipe air. Pipe. It's like pipe air, throttling valve. Okay, so this one maybe not applicable in for aircraft engine, but applicable for fluid mechanic. Okay, mechanical background. Okay, throttling valves are any kind of flow restricting device that cause a significant pressure drop in the fluid. Okay, so any device, any component that kind of restricted means the area is being reduced. Once if you reduce the area, does the volume reduce, something like that. Okay, any kind of flow restricting device that cause a significant pressure drop, so this will cause decrease in pressure drop. Okay, due to the restriction of the flow. What is the difference between a turbine and a throttling valve? Okay, the pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and air conditioning application. Okay, for air conditioning and refrigerator, of course, the function is to cool the room, to cool the refrigerator. Okay, so if we have this valve, throttling valve, when we restrict the flow, means that we drop the pressure. So if the pressure is dropped, then the temperature is being dropped as well. So it is uh, good for cooling purpose. Okay, so the energy balance, the energy balance for this device, throttling valves. Okay, so we only have the flow internal energy, only the enthalpy. Okay, so enthalpy again is, what is enthalpy? Enthalpy is the internal energy, internal, the energy with inside the system, and the flow energy. Okay, flow energy is energy due to the pressure, PV, and volume. Okay, so only that. Okay, there is no work, there is no heat transfer. Okay, for this valve. Okay, only temperature change, pressure change. Yeah. But internal and flow energy may be converted to each other. Okay, so only the internal energy and flow energy only change within inside the valve, the system. Okay, next, other components, mixing chamber. Okay, mixing chamber. Mixing chamber for power plant, of course, there is. We can use, and for aircraft engine, sometimes there is some sort of this mixing chamber. Sometimes because in aircraft engine, why do we need this? But not all, not all engines, not all aircraft engine. But where we have this, for example, in turbofan engine, can I explain? Okay, turbofan engine, we have uh, two sep- two separate flow actually in the engine. One that goes along the core engine, the combustion chamber, etc. Like the gas turbine tadi. Sekejap, I show back uh, the photo so that maybe you can understand clearly. Okay, but don't worry, this one you will learn in propulsion. Okay, just want to explain the function of the mixing chamber if we have in a turbofan. So if you have a turbofan engine, there are two duct flow, duct, 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 bukan DUCK. Okay, duct flow. Okay, there are two duct flow in a turbofan engine. One that will goes through the core engine. This is the core engine. Core engine, compressor, combustion chamber, turbine. That is what we call core engine. CORE, core, the main duct. And the other duct is for bypass fan airflow. So air will flow along this bypass, okay, fan. Okay, there will be fan, and so there will be another separate duct flow. Okay, so but at the end, after exiting the turbine, at the end, these two flow, the flow from the core engine and the flow from the this bypass, which is from the fan, okay, will meet together, kind of meet together, jumpa balik sama-sama. Okay, so some of them, so that's what some of them remain separate until at the end of the nozzle. Okay, and there are some also that will be mixed. These two flow from the fan and from the core engine will be mixed before goes into nozzle. So that some of the turbofan has a, we call it as a mixed flow turbofan, or some of them are separate flow. Okay, so if you have a mixed flow turbofan, then there will be some sort of this kind of mixing chamber to mix the two flow. Okay. Okay, so but in power plant also we can use this more often. Okay, so in engineering application, the section where the mixing process takes place is commonly referred to as a mixing chamber. Okay, like combustion chamber is for combustor, so mixing chamber is for mixing. Okay, so we have like the our shower, water shower here. So we the water, the hot water and the cold water is being mixed. Okay, before it can enters the duct here, and we can use it to shower ourselves. Okay, we cannot just shower with cold water. We cannot just shower with hot water. So we have to mix both of them, both of these hot and cold, to get a warmer water for us to shower. Okay, so this part is the some sort of a mixing chamber. It doesn't has to be rectangular like this. So anything that mix the section or anything that can mix two process of flow, then we refer it as a mixing chamber. Okay, bila kata chamber tak semestinya dia mesti kena ada kotak ataupun satu macam bilik kebuk tu macam tu, tak. Okay, So energy balance for the adiabatic mixing chamber in the figure is, so the energy balance on the energy transfer by mass and enthalpy. Okay, so there is no work done or work input, and there is no heat transfer, or very negligible. Can be negligible, okay? Heat transfer can be negligible, no work output, no kinetic energy, okay? No acceleration or anything, change in any significant change in velocity, and no change in pressure. Okay, we can assume pressure. Potential energy. We can assume the potential energy is negligible. Actually, of course, if you see like this, if you ask me, um, uh, like the level, the height for this output is different than the height of this, both of this input, right? But the height is negligible compared to the this internal energy change. Okay, it's not that there is no potential energy, no change in altitude. Tak adalah dia macam satu level je. Of course tak. Tapi but the potential energy can be negliged. Okay. Next is heat. Saya ada berapa lagi? Okay. Okay, next is heat exchanger. Heat exchanger. Okay. So heat exchanger is quite important as well. Okay, so what is a heat exchanger? So heat exchanger are devices where two moving fluid stream exchange heat without mixing. Kalau ni tak mix So the difference between heat exchanger and the mixing chamber just now. Mixing chamber So they kind of mix together, like the hot and cold water here. They goes into this dark pipe and they mix with each other. Okay, normally they are in the same substance, water and water normally, walaupun tak wajib. Okay, water, so they mix around. Okay, but for heat exchanger, they exchange heat but without mixing. Okay, so one fluid will goes along the pipe, another fluid will flow just outside it. Okay, outside of the pipe, but within the chamber here. Okay, within the device. Okay, okay, so that is the difference between one of the difference between mixing chamber and heat exchanger. So this is important as well in power plant and for aircraft. So we have fluid A. Normally it is if you have gas, vapor and or steam with liquid, water, etc. So the liquid will be flowing in the like the fluid A. Okay, liquid will be flowing along the pipe here, the duct here. Okay, fluid A. And the steam or the vapor, the gas will flow inside the chamber or the device here, but outside of the pipe, we circulating the pipe, the duct. Okay, so the heat, the convection, okay, convection process, heat transfer will occur. Okay, because the fluid B is in higher temperature, 70 degrees Celsius, and fluid A is 20 degrees Celsius. Okay, so remember the heat transfer process is always from the high temperature fluid, higher temperature device to a lower temperature device. Okay, tak boleh, cannot be from fluid A to fluid B. It is from fluid B to fluid A because fluid B has higher temperature, of course. And we imagine it has the molecules inside within the fluid B has a high kinetic energy, so they are the one who's going to transfer heat to the lower temperature fluid. Okay, So at the end, at the exit, what happened is that the fluid A is going to increase the temperature to 50 degrees Celsius, and fluid B is will be cool, will be cooled down uh, to lower temperature, because it already give heat to the fluid A. Okay, so fluid B will become will decrease in temperature to around, for example, here 35 degrees Celsius. Okay, so that is the function of heat exchange. And normally this one heat exchange or like the evaporator just now. I give you example of evaporator. Um, you have so the fluid A will be the working fluid of in the cycle evaporation. Okay, and that means that we need a heat source from outside, which is fluid B. This heat source comes from fluid B. um Tak apalah. Okay. Tak apa, saya kena lukis, tak apa. Okay, this heat source come from fluid B. So fluid B will give energy, heat to the fluid A, so that fluid A can evaporate, can heat up, increase temperature from 20 to 50 degrees Celsius. Okay, example evaporation process. And then this one. Okay, so the process is within a closed control volume, a closed system. Okay, so we consider the heat exchanger is in a control volume boundary. Okay, the heat transfer associated with the heat exchanger may be zero or non-zero depending on how the control volume is selected. Okay, so depends on um, the control volume, the system that we choose. Okay, because sometimes like kat sini it's mentioned here. Okay, maybe zero or non-zero. Okay, sometimes the heat transfer means that the total heat given by B, all of the heat is going to be received by fluid A. So the heat transfer will be zero. Means, for example, if fluid B has 10, 10 kilojoule of heat, and all of this 10 kilojoule is being being transferred to fluid A, and fluid A will increase in temperature. Okay, so the heat transfer of the system is zero. But sometimes maybe fluid B only give some portion, only some part of its energy, maybe only 5 kilojoule out of the 10 just now to the fluid A. Okay, so that what it mean. Mass energy balance for the adiabatic heat exchanger in the figure. Okay, so the mass energy balance for this system. Okay, so only enthalpy, mass balance, energy transfer by mass, enthalpy here. No work input or output, and no heat input or heat output. Okay, even though there is heat transfer from fluid A to fluid B, okay, but we consider is that it is the within the system, inside the system, bukan from outside. Okay, so kalau dia if it's from outside, then we have Q in lah, Q in or Q out. Okay, but here we define the control volume, include all of the system, including the heat from the fluid B or from the water here. Okay, so it is included in the control volume. Okay, it's okay. Okay, we will see in the tutorial later on. And then pipe and duct flow. So the transport of liquid, 10:17. The transport of liquids. So I finish with this slide and then we take a break. Okay. Pipe and duct flow. The transport of liquids or gas in pipes and ducts is of great importance. Okay. So pipe. So actually the function is more or less the same. Okay. Pipe is used to transport the liquid or gas. Okay. And it may involve some sort of work. Okay. So work transfer by shaft. Okay, so they have a shaft work or resistance, electrical resistance. So there is electricity work input there. Okay. So heat being lost. So for pipe or duct flow, we kind of have all these energy transfer by work, heat and enthalpy, mass. So heat loss from a hot fluid flowing through an uninsulated pipe or duct to the cooler environment may be very significant. Okay, so we cannot neglect the heat output or input of the system pipe duct. Just now, this one, heat exchanger, it's mentioned here that the mass and energy balance for the adiabatic heat exchanger. Adiabatic means that we consider the system kind of like insulated. Means that it doesn't change heat with the outside of the control volume. Okay, it only change heat within inside the control volume, the heat exchanger. Okay, so that's why there is no heat input Q in or Q out. We consider it an adiabatic heat exchanger. If the heat exchanger is not adiabatic, then there must be some sort of a Q in or Q out. Okay, means that the control volume, the system change heat with the surrounding. Okay, this one is uninsulated, for example. Okay, uninsulated means it can change heat with the environment, cleaning their surroundings. Okay, so we have this Q. Okay, Q out. Okay, so I think we take a break now. It's already 10:17, 10:16. Okay lah. Okay, whatever. Okay, so we take a break 10:16. 10:16, sorry. 15 minutes, maybe until 10:30. Okay, 10:30, 10:31 macam tu. Okay, we take a break. We come back at 10:30. Okay, sorry to keep you waiting. Sorry. Okay, tadi sikit. Okay, can we continue? I have only two slides left, and then we can do exercise tutorial. Okay, present back. Okay, so finish with the energy balance of each of the device. Okay, so now last part is the okay, energy analysis of unsteady flow. Okay, just now we consider the process is in a steady flow process. Okay, means that the all the properties, pressure, mass, etc. Doesn't change with time. Okay, but here for unsteady flow process, the control volume change. Okay, the all the properties inside the control volume change with time. Okay, but however, most of the unsteady flow process can be represented reasonably well by the uniform flow process. Okay, so what is the uniform flow process? Okay, means that we can consider this unsteady flow as uniform flow, flowing uniformly like that. Okay, the fluid flow at any inlet or exit is uniform and steady, and thus the fluid properties do not change with time or position over the cross section of an inlet or exit. If they do, they are averaged and treated as constants for the entire process. Okay, so this means that for unsteady flow process, we can still consider it as uniform flow. So means that when we say that it is uniform means, okay, the property still change within time, but the change is within the closed system. Okay, within the inside the area. Okay, so what we have for the mass balance and the energy balance, okay, M in minus M out is equals to the change of the mass throughout the system, throughout the control system. Okay, instead of just now, M in minus M out is 0, so M in equals to M out. But here we have M in minus M out is the change of the mass within the system. Okay, inlet or outlet or final or initial. Okay, the same for energy balance. We have E in minus E out equals to the change in energy, okay, internal kinetic potential energy of the system. Okay, the change is no longer zero, but we can still use this energy balance equation, but the inlet minus outlet is equal to the change of energy of the whole system. Okay, so this is the what our energy balance will look like. Okay, we can use this one for unsteady flow process. Okay, now the more interesting part is the example exercise. Okay, so last week, I will create a Jamboard so that you try to think about it first, and then we will try to solve it together. I will call someone to try to solve it also. Edit the link sharing on. Anyone with the link can view. Anyone with the link. Okay. Mana tadi? Okay. Kena edit ni. Change. Anyone with the link. Viewer editor. Done. Okay. Okay, so we look at the first questions. A piston cylinder device contains 25 grams saturated water vapor that is maintained at a constant pressure of 300 kilopascal. A resistance heater within the cylinder is turned on and pass a current of 0.2 ampere for 5 minutes from a 120 volt source. So there is electricity resistance heater. At the same time, a heat loss of 3.7 kilojoule occurs. Okay, ada heat loss. Okay, A show that for a closed system, the boundary work, okay, remember what we have learned last week. Okay, so that's why I say that towards this chapter, actually we apply all the theory concept that we have learned in the previous chapters. And the change in internal energy, delta U, in the first law relation can be combined into one term, delta H, for constant pressure process. Okay, so the question A is not yet calculation, but you need to redefine the energy balance equation. Okay, define the energy balance equation for this situation. Okay, not yet calculation. Okay, 1A means that you apply the energy balance equation to the system, to the water piston cylinder, and see how you get the expression for energy balance. Okay, part B, then we will calculate. Okay, and we will use the table that we have before, table A5. And if we need others, I will give, I will share. Oh, you can search also, Google je, okay? So first part dulu, first part first, A, just rederive the energy balance of the system. Okay, try to think about it. Maybe I will call someone. Okay, actually the first part you have to show that the change in internal energy. Okay, apa ayat dia? Show that for a closed system, the boundary work and the change in internal energy in the first law relation can be combined into one term, which is equals to delta H, the change in enthalpy. For a constant pressure process. Okay, this is the condition, constant pressure process. So you have to prove that this is equal to this. Okay, okay, this is the one that we have to prove. Saya tak tunjuk yang ni. Okay, this is the one that we have to prove. Okay, that delta U, the change in internal energy, is equal to the change plus a boundary work that we have learned last week, is equals to the change in enthalpy by using the first law energy balance definition. Okay, remember energy balance, we have heat, power or work, and then we have enthalpy, H, and then potential energy, kinetic energy. Okay. Okay, go back to the questions. Okay, process cylinder device contains 25 grams saturated water vapor that is maintained at constant pressure. Okay, so for this one, okay, first we write our energy equation. Tengok balik ni. Okay, there is work. First, heat transfer. Heat transfer to the system. And the W is the work done to the system. And we have delta U, the change in internal energy, and the change in kinetic energy, plus the change in potential energy. Okay, but here we assume both of these is zero. Okay, there is no kinetic energy and there is no potential energy. Okay, now for this work, we have several types of work in this process. One is the electric, because we have a resistance heater. So we have electrical work, and then we also have the shaft work. Okay, shaft to rotate the rotating within the water. Okay, so and then the boundary work. Okay, because of the piston will have some sort of a pressure. Okay, a pressure. So there will be a boundary work done within the system. Okay, so Q. Ini saya explain dulu B nanti application. We try to do it. Okay, B, W. which is chef work, electricity work, okay? B is the boundary work, equals to delta U, okay? And then okay, so this we want to define this boundary work. Okay, this boundary work can be defined. Remember, work is integral. Last week, work is bukan macam ni. Sorry. Work is the integral of PdV, right? Okay, but here we have we know that P is constant pressure, so we can take out P and we just integrate V. Okay, just integrate V, so V, the change in V, V2 minus V1, or V final minus V initial. Okay, so for this process, the boundary work is P V2 minus V1. We can put it here. Okay, boundary work due to the constant pressure. Okay, so now, okay, since that the pressure is constant at 300 kilopascal, so pressure, like initial pressure, constant throughout the process, so means that the pressure is equals to the P1, P2, or P in, P final. Okay, P in, P final, P initial, P final. Okay, so because P is constant, so we can rewrite this equation, this energy balance, Q minus W due to the electricity and other stuff, equals to P delta V, delta U, okay, tak plus itu. Delta U plus P delta V, which is also equals to, we can also write it as U, inlet and outlet, initial and final, U plus P to V2 plus U1 P1 V1. Okay, because P2 P1 is the same. Okay, which is equals to the P initial. Okay, so we can, if we can write it like this, P2, even though it's the same value, and V2 V1. Okay, so this one, this part and this part is the H enthalpy, H2 minus H1. So H2 minus H1 is the change in enthalpy. H2 minus H1, so equals to delta H. Okay, delta H, Q minus W other. Oh, again, betul lah, H tu ni. Okay. Okay, so we already put the internal energy part and the boundary work equal to the delta H, this part. Okay, this part that we have to show. Okay, so boundary work and the internal energy equals to the enthalpy. Okay, we don't have to calculate yet. Okay, the second one, the second part, this one you have to calculate. Okay, determine the final temperature of the steam. Means T2. T2 or T final, TF. T2 or TF. Okay, this one you try. Determine the final temperature of the steam. T2 or T final. You have to use table, the saturated table, water. If you don't have it, you can look at our WhatsApp group before that. 2 weeks ago, I've shared some of the table. The first one is the table A5 saturated water. Okay, you can use that one. Table satu lagi. I need to give you another table for the final part yang but for the initial part, one, you can use the table A5 already in the WhatsApp group. Okay. This one another table untuk final state table A6. Okay, you can start by calculating the electrical work done. Electrical work, voltage, current, and the time 5 minutes. You can change into second. So that is electrical work. That is one part. Okay, another part that we have to calculate is the enthalpy. Okay, because of the definition we have just now. E into R. Okay, I will call someone just to calculate electrical work first. Okay, Amirul Akmal, are you there? Amirul Akmal.
Yes, doctor.
Okay, boleh calculate yang electrical work dulu. Kau awak dah calculate yang energy yang ni lah question number 2.
Belum tu.
Kalau okay, buat yang electrical work. Electrical work simple je, masuk formula je. So boleh buat boleh buka Jamboard tu, whiteboard tu.
Sebab internet slow tu kat sini tu. Saya tak boleh nak. Saya
Tak boleh
dengar je.
masuk.
Dia internet kat bilik ni memang.
Okay, tak apa. Bagi tahu electrical work tu apa, macam mana kira dia? Electrical work. WE. WE ni. Work due to the electric. Yang ni easier lah than nak calculate enthalpy nanti tu.
Jangan saya nak refer note.
For others, please think about the by using the energy balance yang ni kan nanti kan. This one, we have this one. Okay, you need to calculate the enthalpy. Okay, in order to get the temperature. Okay, because the temperature is inside this enthalpy definition. Okay, so use this energy balance equation. So and later on we just add the electrical work to the equation.
Excuse me, Doctor.
Yes.
Macam mana nak guna table S6 tu?
Okay. A5 yang first initial part tu dah untuk H1 dah. Sebab yang
Dah.
H1 guna table A5 dulu,
A5.
yang table last 2 weeks bagi. Yang tu dah?
Dah.
Oh dah okay. So the second part okay, it's because from the first H1 tu, okay, let's explain okay, because you have to calculate you will get H2 enthalpy at the final state first by using table A5 tu. Table A5 is to get the enthalpy initial H1. Kan? You use the table A5 yang last 2 weeks saya bagi untuk dapat H1. To get H1. Okay? Once you get H1, you substitute in the energy balance equation. Okay, with the work, electrical works, all of this, energy loss, heat loss semua, and you will get H2 by calculation, not table yet. By calculation, you will get H2. Okay, so once you get H2, and then you use the table A6 that I just sent to you. Okay, so the table A6 means that you have to search. We know the pressure. The pressure is 300 kilopascal. Because saya terbalik itu the pressure at this state is 300 kilopascal. 300 kilopascal equals to how much? 0.3 megapascal. Kan? 300 kilopascal, 0.3 megapascal. So from the table A6, you look at the column, the box P 0.3 megapascal. So you search for the nearest enthalpy that you have calculated H2 tu.
Oh, okay.
Maybe you won't get the exact value the same, tapi kita cari yang nearest. Ataupun sebenarnya kita boleh extrapolate juga. Extrapolate kan point tu, tapi tak apalah kat sini kita tak buat extrapolation. We don't do the extrapolation. If we want to precisely measure the temperature, we can extrapolate the table. Okay. Otherwise, just search for the nearest enthalpy that we have calculated. Look at the table at pressure 0.3 megapascal because 300 kilopascal equal to 0.3 megapascal. Okay, and from search for the value enthalpy that you have calculated, the nearest possible value, and look at the temperature. Temperature tu berapa? So that is your T2 temperature.
Okay. Dapat.
Okay.
Thank you, Doctor.
Okay. Yes, Syed.
Can you share us the notes, because we don't know all the givens. I don't remember all the numbers just now. So
The
is it okay
number.
if you?
Oh, okay.
Yeah.
Okay.
Yes. Because we can't.
The questions. The questions.
Yes.
Okay. Because okay, since apa tadi, Akmal, Mirul Akmal cannot write. Okay, you just tell me how do you calculate the electrical work first.
Is it W is equal VT?
VT and
N?
takkan V darab T je. Ada lagi.
Yep.
Voltage times apa time. Voltage multiplies lagi satu lagi. Because voltage dengan time baru volt and seconds kan.
Q lah tu.
Tak. Ni ada dalam ayat tu. Turn on and pass a current of 0.2 ampere.
Oh, ampere tu.
Current. So 120 volt multiply with 0.2 ampere and multiply with the time 5 minutes change to seconds, so 300 seconds. So you get electrical power in joule or kilojoule. Okay, but I advise you to change into kilojoule because you need to use the table. Tables is in kilojoule, and the heat loss also given in kilojoule. So change it into kilojoule, so you get 7.2 kilojoule or 7,200 joule for electrical work.
Okay.
Okay, so that is just one part. And then untuk enthalpy ni, you need to use the energy balance that we have stated for A. Actually, for the energy balance, I think it's better the sign for W electrical and Q out. It's better to imagine that our system is the water inside the cylinder. So means that we receive work from the electric. So the electric in positive, and then Q out, key heat loss, negative form. Okay, because of the heat loss, and then the boundary work is still negative. Okay, so like this. Sini tadi, this one is 7.2. Okay, 7.2 kilojoule. Okay, so the relation just now that we have, W, I change to electrical, minus Q out, heat loss. The boundary work is still boundary work done by the piston, okay, by the system, and change to it equals to the delta H. So delta H is M, H2 minus H1. Okay, M is the mass. Okay, so okay, before we can proceed this energy balance calculation, we need to find H1 first. H1 can be found from the table A5. Table A5, saturated water, we can search for H1. Mass is given, WB we can calculate, WE already calculated, and Q out is given. So we don't know enthalpy, both of these enthalpy, but we can solve the H1 first. Because H1, we know that the at state 1, the pressure is 300 kilopascal. Okay, and we know that the water is at saturated water vapor. It is stated here, a piston cylinder device contains 25 grams saturated water vapor. So means that we can use the table while the water is at saturated. Okay, saturated condition. If I show you, saya tunjuk yang H1 dulu. Okay. Okay, this is this one lah. So P1 300 kilopascal. 300 kilopascal. This one is in kilopascal. The other one is in megapascal. So please make sure that. So 300 kilopascal. This one, this line, this row. Okay, and saturated vapor. We are already at saturated water vapor. Okay, table. And then so H1. So we can find H1. H1. Saturated vapor. Okay, saturated vapor H1. So 2724.9. Saturated vapor. Saturated vapor 2724.9. So this one is H1. Besar sikit. Okay, H1. H1 to 724.9. So substitute this value inside here. So WE 7.2 minus 3.7 heat loss. Boundary work. Boundary work. Be constant je. Okay, boundary work is already included in the work electrical just now. Okay, so no, boundary work is already in the enthalpy. Okay, so actually tak payah klik dah. Okay, this one because you already included in this one. Just now we already included. Pening dah saya pun. Because since we change the U plus PV equals to enthalpy, so no longer there's no longer boundary work here. So it's like, okay, so equals to mass 0.025 kilogram, and so H2, the one that we need to calculate, minus H1 27 number 27
2724.
2725 or 2724.9, 2725 kilojoule. So make sure kilojoule. So you get H2. Okay, around 2865 kilojoule per kilogram. Okay, you need to put the
Doctor,
unit. Yeah.
where you get 3.7
3.7 is in the question.
in the question? Okay.
At the same time, a heat loss of 3.7 kilojoule occurs.
Okay.
Okay, and then by using this H2 value, we look at the table A6 just given. Okay, so table A6 yang tadi Afiq tanya. Okay, okay, this one. So table A6. Constant pressure. So we know that the pressure at the state 2 or final is still 300 kilopascal or 0.3 megapascal. So we look at this box, only this box. Okay. And so 300 and then H2 2865. Okay. So we get H enthalpy. Okay, this table, we don't need to define whether H is HF or HG fluid gas just now, because we already know that the water is superheated. If the water is superheated, it means that it is in a vapor form. Okay, dia takkan liquid form. Liquid tu tak superheat. Kalau superheated tu memang water tu dalam vapor lah, dia bukan dalam liquid dah. Sorry, I lost my connection. Okay, sorry. Okay. Oh, come on. Just now, I don't know, you guys follow me until when?
Table
You start
doctor,
at
table.
with
Table,
0.3 megapascal.
Okay. So this one kan 2x is 5. If we extrapolate the table, maybe we get the temperature 198 degree or 195 degree kan. But it's okay here. We just take the nearest possible value. 2x is 5.9, so equals to 200 degrees Celsius. So that is the answer for T2, T final. Okay, 200 degree.
Yeah, I'm sorry, miss. Can you repeat this last part?
Oh, repeat again. Okay, so H2 you calculate from the energy balance just now. This one, right? You calculate H2, you get 2x is 5 kilojoule per kilogram. Okay, so okay, that's why you have to understand the situation. Okay, the water is in the cylinder. When we give the resistant heater, means that we heat the water. Okay, it's initially it's already in at saturated vapor point, and if we heat it more, it will be superheated vapor. Okay, it will no longer return to liquid or anything. Okay, so it is at the final state, it will be in a superheated vapor. So we have H2 and we know pressure too, because pressure constant. Okay, so we can use this table acid or superheated water. Okay, even though it is called superheated water, water here, it doesn't mean that it has to be in liquid form. Water here is the substance. So that's why we need to learn first the properties, the definition, etc. Because water here doesn't mean it is in liquid. It is a substance. The substance is water, H2O. But it is in superheated form. So superheated, it must be a vapor. It cannot be a liquid. Superheated water is vapor. So no need to define HF or HG or the quality X, because we know the whole of this table are in a vapor form. Okay, the substance water is in vapor. So, and it is heated. Okay, the piston, the water is heated. So obviously it will become more and more as a vapor, not as a liquid. So we just take the nearest possible value to X is 5. We have this one. Okay, and we look at the temperature. Temperature is 200 degrees Celsius. So that is the final temperature, T2 or TF, the final. Okay? Okay, Marwan.
Oh, thank you, doctor.
Okay. The others, Khairul Rushdi, okay, Miza. Boleh follow? Setakat sekarang. Can you guys follow?
Okay, doctor.
Doktor tadi soalan minta apa lah?
T final, T2.
T2. So sekarang ni 200
Degree.
Celsius.
Habis lah. Habis lah 200 Yang tu je lah jawapan dia.
Oh, okay.
Yang kita kena calculate H2 tadi. We have to calculate a H2, H final. Okay, using the energy balance equation, we calculate H final. And we use the table. By using the table, we no longer need to calculate temperature. We just read the table, read the temperature. Okay, we read the temperature dalam box ni. Okay, because pressure 300 kilopascal or 0.3 megapascal. Okay, superheated water because initially the water is at vapor, saturated water vapor. So if we give heat up guna resistant heater tu, of course kita heat dia. So bila kita heat, dia lagi lah akan jadi vapor, dia tak akan jadi liquid pun. So boleh directly guna table ni. Okay. Okay, imagine if you remember chapter 2, chapter 3, we have kind of like this PV diagram, kan? So saturated vapor is along this line, kan? Ni saturated vapor. Okay, so initially it's already at the saturated vapor line. So if we heat up, it will become superheated vapor. In the diagram, dia akan duduk sini. Saturated vapor along this line, superheated vapor outside of the line lah, but on the right hand side. It will not go back to this because we heat. Okay, guna resistance. Okay, next. Saya tak share type. Okay, so because we heat, I'm explaining these figures. Okay, because we heat, this is the PV diagram. Imagine the PV diagram that we have chapter 2, chapter 3, something like that. Okay, about the substance. So we have the water initially at the saturated vapor line, and then we heat up again, so it becomes superheated. It will not be in the liquid part. Okay. Okay, next. Lama side nombor 1. Okay, next is the question. Okay. Again, piston. Okay, piston cylinder device initially contains air at 150 kilopascal and 37 degrees Celsius. At this state, the piston is resting on a pair of stops, and the enclosed volume is 400 liter. Okay, the mass of the piston is such that a 350 kilopascal pressure is required to move it. The air is now heated until its volume has doubled. Okay, double volume, final 2V. Determine the final temperature, the work done by the air, the total heat transfer to the air. Okay, so try to analyze this problem to understand first. Penat saya cakap. Okay, for these questions, actually kind of have state 1, state 2 and state 3. Macam ada two different process. Because from the first initial state to the second state, okay, the piston is resting. Okay, that is from one part to the second state. The piston resting, and then we put pressure. Okay, and the air from 2 to 3, the air is heated until its volume is double. Okay, so if you want to illustrate the process from 1 to 2 and 2 to 3. If you can try to sketch the PV diagram, pressure versus volume, so that you can see whether the pressure change or the volume change within the process. and usually you try to name first. For example, 150 kilopascal is what? Pressure at which point? Initial, right? So initial, write it P1, 150 kilopascal. Just rewrite back all the rearrange all the values so that you can see clearly the problem, which value that you have, which value you don't have that you need to calculate, that you can derive from the equation, etc. etc. So we have P1, 550 kilopascal, and we have T1, temperature 27 degrees Celsius, T1. Okay, so initially the volume is 400 liter. So 400 liter, change it to meter cube. Change to meter cube, meter padu, because our SI units for calculation is in meter cube. Okay, change the 400 liter to meter cube. Google je, convert je. Okay. Sorry.
Doctor,
Yeah.
temperature, do we need to change to Kelvin?
Yeah. Lupa pula. Temperature in Kelvin, because if you want to use the ideal gas equation, etc., kena dalam Kelvin.
Okay, thank you, Doctor.
Memang SI unit sebenarnya dalam Kelvin lah. Okay, change the temperature ni. Okay, I just help you to illustrate the process. Okay, imagine you have a PV diagram. Since we have constant pressure, constant volume process, so it's easier to sketch it. So we have P, V here in meter cube. So initially, 150 kilopascal, 27 degrees Celsius. Okay, so this one we write it as 150. And we have another information on the final pressure, so it must be 350 here for the final pressure. Okay, and then what else? Temperature, no need in this diagram. We just need the volume. So initially the volume is 400 liter, which is around 0.4 meter cube. This 1 kilopascal. Okay, so at this point, okay, so this is point 1, initial state 1, and then at this state, the piston is resting on a pair of stops and the enclosed volume is 400 liter. The mass of the piston is such that a 350 kilopascal pressure is required to move it. Okay, so the pressure is changed to 350 kilopascal. To state 2. Okay, but the volume at this point still the same. Okay. And then the air is now heated until its volume has doubled. Okay, so we heat the piston, the air inside within the piston, 2.3 at constant pressure. Okay. Heated, volume double, so 0.8. Okay, 0.3. Okay, so the process from point 1 to 2 and then 2 to 3. At 2 to 3 at constant pressure, because we don't add any pressure anymore to the piston. Only from point 1 to point 2, we add pressure, and then when we heat the air, the piston, okay, only the volume is changed, volume is double. Okay, so we calculate first one, the final temperature. Second one, the work done. And the third one is the total heat transfer. The total heat transfer, then you use the energy balance equation. For A and B, you don't need actually the energy balance yet. So to calculate final temperature, yang first one, the first one, you can use ideal gas. Okay, ideal gas equation of state yang PV equals to RT. Okay, final gas, ideal gas equation between state 1 and state 3, because we have the parameters, the information on state 1 and state 3. you want to know the final temperature, which is T3. Okay, we know P1, T1, 150 and 27 degrees Celsius, so change into Kelvin. And then P3, T3, P3 is 350 kilopascal. And T3 is what we are going to calculate. And then volume, we know that the volume is double. Double. So you use the PV/RT. R is constant, so you can just cut it out, the ideal gas equation. So you can get the T3, the temperature final. Saya tengah cari satu lagi table for the energy balance calculation. Maybe we just finish exercise 2 dulu. Sampai 2 exercise ni. Okay. So we use the equation state ideal gas equation state. Ideal gas equation state PV, saya tulis dulu takut ada lupa. PV MRT or if we use small v, big besar v besar, sorry. Okay, so this one MRT. This is ideal gas equation of state, chapter 3, I think. Okay, ideal gas equation of state. So mass, so between state 1 and state 3, the mass is constant. So we and R also, the gas constant, this parameter also constant. So we can cut this. So between state 1 and state 2, state 3, sorry, we have PV1, P1 V1 T1 equals to P2 P3 final temperature T3. Okay, so P1 is 150, V1 we can V1 is 400 liter or 0.4 meter cube. T1 is 27 degrees, so change it becomes 300 Kelvin. P3 is 350 kilopascal, so V3 is double of that V1, so 0.8. And T3 is what we have to calculate. So what do we get for T3 temperature? Khairul Rushdi, have you calculated? Khairul? T3 final temperature?
Doctor, as
Yeah.
for me, I get 600.3 Kelvin.
T3 600. Takut. Cuba calculate balik. P1 150 kan. Volume tu dah change dalam meter cube 0.4 dengan 0.8.
Meter cube.
0.4 kan.
Mm-mm.
Actually kalau tak tukar pun ke meter cube sebab nanti dia akan potong juga, sama juga. P3 is 350 kilopascal.
P what, Doctor?
Pressure.
Okay, Kia.
Temperature T1 300 Kelvin.
Okay, I made mistake.
1,400 Kelvin, doctor.
Yes. 1,400 1,400. I think this one easy je lah semua everyone try to calculate 1,400 Kelvin. Okay, next. B. The work done. Okay, so the work done is actually like the boundary work, PV. The work done by the air between state 1 to state 2. State 1 to state 3. Okay, state 1 to state 2, V volume constant, so there is no work done boundary. Work boundary done sebab constant volume 1 to 2. But 2 to 3, you have the boundary work, okay. So, or the area from the diagram just now, you can calculate the area. So, WB, okay, this one we have used several times. We have done this several times, so I just write it. So we take P2 or P1 also can. P2 or P3. And then V3 minus V2. Ada soalan. 1,400. Okay,
V1
thank you, Khairul. Okay,
V3 minus V1, or we
okay.
don't know V2, I think.
Sorry?
I think it should be V3 minus V1, or is it V2? Because we don't know V2.
Yes, we can. You can write V3 minus V1, but we know that 1 to 2 constant pressure.
Okay.
So we can just cut it out lah.
Okay.
Okay, so this one, how much? This is 0.4, the difference, and multiply with P2, 350 kilopascal. So, how much? Look at siapa lagi yang diam ni. Miroda, Omar, Al-Mansur Omar. How much do you get the boundary work? Or the work, simply? This work? Omar Mansur, are you there? Next week test.
Yes, doctor.
Okay, sorry. Al-Mansur Omar. So, how much do you get for work?
140 kilojoule.
Okay, thank you very much. 140 kilojoule, okay? We change directly to joule lah. Even though this one is in kilopascal and this one is meter cube, but we can change to kilojoule directly. Okay, so and then C. Okay, finish with C. Okay, so this one you need to use the energy balance. We need to calculate the total heat transfer to the air. So we need to calculate the Q lah, Q in. Okay, Q in. So okay, back to the our definition of energy balance. So we have Q in minus the work boundary work done. Okay, and okay here we use delta U. Actually, if we like the previous question 1, we can also write it as Q in equals to delta H directly. Okay, but since we have calculated this value boundary work for question B, so we separate the internal energy and this one. Okay. Actually, this is enthalpy is internal energy plus boundary work like the previous questions. Okay, but since we have this value, so we will use heat here. So we separate it like this. This one, okay. And no work, ada electrical work or shaft work given, and no kinetic energy, no potential energy. So only this. Okay, so so rewrite the equation. Q in minus WB, the boundary work, mass. So now we use the internal energy instead of enthalpy, because we already separate the boundary work here. Okay. So first mass. Mass kita tak tahu. Mass we don't know. So we calculate using the ideal gas equation. We use initial point lah. Okay. RT1, because we have all the value at initial point. This is the ideal gas equation just now. Okay. Ideal gas equation. Kita guna yang point. We use the initial point lah. Better because the initial point is given. In case we did mistake in the calculation of state 2 or state 3, at least we use the initial point given, but our parameter is always correct. Okay, so P1 is 150 kilopascal, V1 here 0.4, you must use 0.4. 0.4 meter cube, R is 0.287 kilopascal. R is 0.287 kilopascal or 287 pascal or joule. Itu bukan kilopascal, joule. Okay, R itu di sini lah. Okay, R is 287 joule per kilogram per Kelvin. Okay, why I mention kilopascal? Because we have P here. P is in kilopascal. So that inside the joule, we have kilopascal actually inside here. Joule is equals to pascal meter cube. Okay, meter cube. Like this one, joule, pascal, meter cube. Okay, inside here. Okay, so since pressure is in kilopascal, so that's why we change also the R into kilo, 0.287 instead of 287 joule. Okay, so this is in kilojoule because it's easier to divide with the kilopascal here. So 150, 0.4. This one make sure meter cube. You cannot use liter in this equation. And 300 Kelvin. Okay, so you get the mass. Okay, so and the mass is assumed constant throughout the process. Okay, until from 1 to 3. So once you get the mass, okay, you can use include the mass here, and then we need to use another table, okay, for ideal gas to search for U3 and U1. Okay, the one that I just forward. Mana ni? Okay, this one. Okay, look at this together. We are going to finish soon. Okay, please look at this first. Okay, U3 and U1. Okay, U1 first. Okay, U1. This is the ideal gas properties of air. Ideal gas table A17. Ideal gas, because we assume that the air, the air is ideal gas. Okay, ideal gas. Okay, so at state 1, temperature is 300 Kelvin. Kejap ada questions. Okay, okay, correct Marwan. Okay, the mass. Okay, okay, 300 Kelvin to 300 Kelvin. So we look at the U, internal energy. Okay, internal energy is 21407 or 214 kilojoule per kilogram. Okay, U 300 Kelvin, 214.07. Another one for final state 3, T3 that we have calculated for A is 1400. So another page. Sorry, page satu lagi. Okay, page 1400. Okay, 1400 and U is 1113.5. Okay, 113.52. Or take all the decimal value. 0.52. Okay, so this is U3. U final, internal energy at final point. Okay, and so substitute in the in this equation, so you get, okay, saya tulis lah. Okay, Q in the one that we have to measure, minus the boundary work just now 140 kilojoule. We leave it in kilojoule. And then the mass, thank you Marwan. So we have 0.967, 697.
Sorry, that is 97. Sorry, I wrote it wrong.
Okay. Tak apa. I mentioned it wrongly. Okay. And then U3 minus U1, U3 1113.5 minus minus 214.070. Okay. Okay. So just calculate it and you get Q in 767 kilojoule. Okay, in your test or final exam, don't forget to write clearly the unit. Okay, clearly write down clearly the unit, the equation, etc. T1, P1, please define it clearly. Okay, so we if you were to analyze this one, so we get Q in positive value, means that the heat is transferred given to the system. The system, the gas, the gas, the air inside the piston cylinder receive heat. Okay, heat is being transferred to the system because we have the this positive value. Okay, so I think we stop here. This exercise.
Doctor,
Yeah.
why we need to look at ideal gas table?
Because we want to search for you. Otherwise, ada cara.
Oh, memang kat situ je doktor.
Yeah, because we already we have the temperature, okay, and we already assume that the air is ideal gas. So we can calculate U lah.
Okay.
Okay. Okay. Saya stop dulu recording.